それでは続きまして、オーラルプレゼンテーション7、大阪桐蔭高等学校。タイトルが、鉛フリーハライドペロブスカイト型太陽電池の研究。中内亜美さん、森山香乃さん、田尻茂弘さん、東瀬成樹さん。指導は有馬実先生、中島哲人先生、木下光一先生です。それではよろしくお願いいたします。
Hello everyone, we will tell about perovskite solar cells using reed-free perovskite as a light ozone layer. Here's the outline of our speech. Background and motivation. Solar cells which are usually used have several problems. For example, silicon solar cells cause a rot, the liquid of dye-sensitive solar cells escape, and the usual perovskite solar cells are toxic. However, the perovskite solar cells we studied can solve economic and environmental problems. So we would like to research a lot and make these devices as much as we can in high school club activity. In this study, we made perovskite solar cells using lead-free perovskite as a light ozone layer and copper cyanide as a hot transporting material.
Next, mechanism of the perovskite solar cell. In this figure, light enters from the left side and it shines on the perovskite light absorbing layer through the compact TiO2 layer. Then the photogenerated electrons are transferred from the perovskite layer to the phosphorus sensitizer layer, finally to the metal node. On the other hand, after electrons are photogenerated, the holes are transferred from the perovskite layer to the hole conductor layer, finally to the metal cathode.
Next, purpose. Lead perovskite solar cell. We use this as a perovskite light ozone layer. We use spearmethod as a hole transporting material, and we control the thickness of the phosphorus TiO2 layer. Also, we evaluated the solar cells where they are designed to increase hole mobility or go free between hole conductor layer and metal cathode, and then how to work the difference of length to the properties of solar cells. Lead-free perovskite thin perovskite solar cells. We use this as a perovskite light ozone layer to less its toxic, and we use spearmethod as a hole transporting material. Which lead-free perovskite materials are the best for solar cells in terms of short-circuit current and open-circuit voltage? Perovskite solar cells is copper cyanide. We researched whether copper cyanide works as a hole transporting material, and what's the difference between copper cyanide and spearmethod.
Next, methods and fabrication. First, making compact TiO2 layer, spheripyrolysis method. This layer exists in order not to short out because of regurgitating of electrons. We prepared titanium dioxide acetyl acetate. We made ethanol suspension of this precursor. We put the FTO glass on the hot plate at 550 degrees Celsius. The ethanol suspension was got into the glass box, then it was sprayed from airbrush connected to air compressor. We sprayed the suspension in the draft chamber while evacuating the air. We sprayed several times and the compact TiO2 layer was generated. Second, making phosphorus TiO2 layer. The phosphorus TiO2 layer is composed of a few nanometer-sized particles. First, we mix titanium dioxide, polyethylene glycol, and glacial acetic acid. This mixture is called titanium paste. We apply the titanium paste on the glass by glass stick. After drying at 100 degrees Celsius on the hot plate, the TiO2 fumes were gradually heated to 450 degrees Celsius in the electric furnace, back at room temperature gradually. Third, making perovskite layer. According to each experimental coordinate, lead iodide, tin compound, the methylammonium compound are dissolved in the methyl formamide as solvent respectively. We apply this mixture on the FTO glass plate and then anneal the glass in the draft chamber at 100 degrees Celsius. Last, making hole conductor layer. We dissolve sphenometal or copper cyanide as a whole transporting material in chlorobenzene respectively. We mixed 2,6-lutein and lithium-bis compound dopants to increase hull mobility. The dried film thickness was set to 100 nanometer, and we applied this solution on the FTO glass, and then we dried the glass on the hot plate at 100 degrees Celsius.
Next, result and discussion. First, horizontal axis is thickness of the mesopolar TiO2 layer, and vertical axis is voltage. We control the thickness of the mesopolar TiO2 layer. The thinner one has higher voltage. Second, horizontal axis is voltage, and vertical axis is current density. At first, we used spiral melters as a whole conductor layer, but it was changed into doped spiral melter. Dopants are lithium compound. The current and the voltage were improved thanks to the dopants. Next, modification of method in our report. We used the device with dopants. We experimented with the xenon lamp, keeping the device cool by dry ice. Now, I'll tell you how to make lead-free perovskite. We mix Ca3Na3I with SNI2 to make SNI3. We follow the same procedure. First, we succeed in making the device with SNI3. Its open circuit voltage is 142 millivolts, and short circuit current density is 39 microampere per square centimeter. And we achieve making the device with SNBLI2. Its open circuit voltage is 150 millivolts, and short circuit current density is 54 microampere per square centimeter. Second, we succeed in making the device with SNBL2I. Its open circuit voltage is 334 millivolts, and short circuit current density is 30 microampere per square centimeter. And we also achieve making the device with SNBL3. Its open circuit voltage is 250 millivolts, and short circuit current density is 6 microampere per square centimeter. Third, as the Blomer ratio increases, open circuit voltage value increases, and short circuit current value decreases. From now on, we use copper cyanide as whole transporting materials. First, we succeed in making the device with SNBLI2 and spiral melter. Its open circuit voltage is 150 millivolts, and short circuit current is 54 microampere per square centimeter. And we also achieve making the device with copper cyanide. Its open circuit voltage is 49 millivolts, and short circuit current is 21 microampere per square centimeter. Second, we succeed in making the device with SNBL2I and spiral melter. Its open circuit voltage is 334 millivolts, and short circuit current is 30 microampere per square centimeter. And we also achieve making the device with copper cyanide. Its open circuit voltage is 400 millivolts, and short circuit current is 20 microampere per square centimeter. Next, conclusion. First, if we use a 100-watt xenon lamp instead of 650-watt tungsten lamp, both the open circuit voltage and short circuit current, the values increases. If we add the lithium compound as an important dopant to increase whole mobility, the open circuit voltage gets better. In terms of temperature, the device cooled by dry ice works much better than under room temperature. Second, we can make 4 types of lead-free perovskite solar cells using these devices as a perovskite material. These devices are no better than the conventional device with PBI3. The device with SNBL2I marks the largest open circuit voltage value, and the device with SNBL-I2 or greatest short circuit current value. Third, we can ascertain that there is some relation between HOMO-LUMO energy gaps and the voltage and current in the lead-free perovskite solar cells. The larger the energy gap is the open circuit voltage value and the short circuit current density value the device marks. For these reasons, we guess that the device with SNBL-I2 or SNBL-2I, which are the middle value of the energy gaps, have the larger electric power. Last, vertical axis is open circuit voltage, and the green bar graph are the device with spiral method, and blue bar graph are the device with copper cyanide. By using copper cyanide as whole transporting material, we can successfully develop the perovskite solar cells with PBI3, SNBL2I, or SNBL-I2. More surprisingly, the SNBL2I device with copper cyanide marks 20% larger voltage than spiral method. We expect this device an important step towards the realization of low-cost and environmentally friendly device. Next, future works. First, in the lead-free perovskite solar cells, the LUMO level of perovskite material is much below the conductance band level of tantalum oxide. So, if we use the tantalum oxide instead of titanium dioxide, the electromotive force of the device will increase. Second, we use the chemical-based deposition method to make combat TO2 layer, which is done at a lower temperature. To do so, we make the device much better because we can use ITO glass instead of FTO glass. Here is references. Thank you for your kind attention.
ありがとうございました。それでは質疑応答へと移らせていただきます。ご質問のある方、挙手をお願いいたします。質問のある方、はい、ではマイクをお持ちいたします。後方の後ろから3列目の方から参りましょうか。すいません。もう一度手を挙げていただいてよろしいですか。はい、すいません。お渡しさせていただきます。
Hello, it's me again. Okay, can you take back to experiment 1? Can you take the slides to experiment 1? Yeah, that one. So when on here you said that the thickness of the mesoporous titanium oxide layer, when it's thin, then you'll have a higher voltage. But did you think about the thickness of the compact titanium oxide layer? Did you think about that?
Mesoporous TiO2 layer.
Only mesoporous titanium oxide?
In this study, we changed only mesoporous TiO2. We changed the thickness of only mesoporous TiO2 layer, but I think the thickness of compact TiO2 layer will affect the result.
Yeah, I want to see how they will change too. Thank you.
ありがとうございます。その他ご質問のある方いらっしゃいますでしょうか。はい、真ん中の方にお願いいたします。
Thank you for a very impressive presentation. My question is about lead-free perovskite case. And you showed open circuit dependence of open circuit voltage on bromide ratio, and you showed BR2I case has highest voltage. Do you have? Can you explain the reason, or you have a comment on that?
This is because as the bromide ratio increases, the band gap increases. As band gap increases, voltage increases because voltage of semiconductor depends on its band gap. As band gap increases, the amount of available wavelengths decreases, and in terms of current value, decreases.
Thank you. And in phthalocyanin case, BR2I case only BR2I shows increase of voltage. Is it related to band gap?
Yes, it is because band gap.
ありがとうございます。それではお時間も参りましたので以上とさせていただきます。大阪桐蔭高等学校の皆さんでした。ありがとうございました。